Welcome to the last part of the tutorial when we finally find a skeleton for Vivian. Skeletons are easiest to find but hardest to convert because there are so many ways, different ways to represent the bones data in a file. It requires a knowledge of 3D geometry and conversions. So let's look at the files and see where they are. This is our chunk 1. And first we have some names connected to wrinkle maps, which we don't need, hopefully. And after them, we see exactly what we are searching for. This is an array of floating point numbers with a repeating pattern. Here you'll see some zeros, then some number, zeros, number. This is how they look like. There are many bones, so you will never miss it. That's how it's up to here. This is something different here. So probably this table ends here and it go up to somewhere here, probably. So this is the length of it. So it repeats every 3 lines, so 30 in hex bytes. So if we divide this by 30, we'll get a count of elements in this table. And notice this C5, this is probably a count of elements here. So if we multiply C5 by 40, the size might be like this. So we just made a little mistake, it's like this. So we have C5 elements, C5 bones, probably. Now we need to load these numbers and see how they will build up. In this file, it looks like the first line has 3 ones, like 1, 1, 1, and 0 here. So this is probably scale. They will be the same for each bone. This must be scales, and they are all ones. Next 4 numbers, they will always be different. Like, for example, let's take this bone. You see 4 different numbers, and when you load them up in your program, they will be between 0 and 1 and -1, which is a good sign. It can be a quaternion or quad for short. If you make sum of a squares, this will be equal to 1, and this means this is actually a rotation represented as quad. And these 3 last numbers will definitely be coordinates. Like 3 numbers, this is always be 0. Now the only thing we are missing is a parent list to connect the bones between them. We can look for that. So this is some irregular structures, probably those wrinkle marks I never seen how they look like. We don't need them. And after them, what is this? Another regular structure, it looks like. Probably a different... Oh, this is now something that looks like a parent list. It's always easy to find because there will be numbers, small numbers, starting from -1. This FFs is -1. And C5 here again. So probably this number will be a parent number. Sometimes there are only parent indices and nothing else. But in this game we see some flags here and something. Maybe this can be a mirror bone, and this may be an end of bone chain or something. Sometimes it contains a list of childs, but we only need this first number, a parent index, to build the skeleton. So it looks like we found everything we need for it. Later, we can search for its offset, starting here or maybe here, and then go up to the header and find where we have the offset of a skeleton. It will be here. And these numbers will mean something. Or we can go from the header, check all these offsets and find which one of them will lead us to bone data and parent list. But right now, let's just load all these numbers and see how they look like. Well, apparently it's incorrect. You see face looking one side, feet different side, arms are both to one side and distorted somehow. This is and it's all upside down. This is because there are many ways to represent where the X, Y, and Z axis will be. Some games, engines, they have it like X, Y, and Z. Some will have X, Y up and Z here. And this leads to things like this. So we probably just change some components of quaternions and bone coordinates until we'll get the proper skeleton. Of course, you can try to analyze going from the root bone to next bone in a skeleton structure and try to understand exactly what is wrong and how do you switch, which numbers will you switch, or just try this one by one and finally find the combination you need. So let's try something. Oh, this one looks much better. I just switched Y and Z axis and it's lined on the back, but that's usual for SMD skeletons like I represent them. This looks like a correct skeleton now. Built from quads. So now we need to load our model and check if it will work. Okay, it corresponds. Let's try moving something. And it's not correct, but there are good news and bad news. At least we can see that moving the hand moves proper parts of a model, but not all vertices are moving. That probably means that this is just a basic skeleton. You see only 3 bones here. There must be lots of helpers here, and we've seen that in bone names list. So there is something, there must be something else in the file. But good thing is that it looks like we don't have bone remaps here. Like I told in the first part, in the old games, developers needed to split the model into many parts. And it worked like that. Let's take left hand, left arm, maybe, and they will have bone indices like 0 for this, 1, 2, and so on. Now right arm will have, again, bones number 0, 1, 2, and so on. And then to connect this to the skeleton, we needed a bone remap, a number of tables that will allow us to connect all parts together to work as a single skeleton. But in this case, in this game, we don't have this. We have the whole skeleton connected with bone IDs right from the skeleton. So this bone number 17 is actually a shoulder bone. And this other shoulder is bone number 18 and nothing else. We have lots of face bones too, and they will all work correctly, I think. We just don't have helper bones for some reason. So let's return to our file and try to find something else that will help us to build the whole skeleton. Well, this is our parent list. And remember, right before it, we had another repeating patterns of floating point numbers. This must be another bone table. So let's try finding it somewhere here. It must start. And it will go down there. These look like random bytes, and these are still floating point numbers, and these small numbers here, so it's probably ending somewhere here. And again, the period is 3 lines, so we must have the same size of each element here. So the total size will be something like 110 in hex, which is that many bones. Let's try returning to the header. And we have this number here too, right at the beginning of the file. And if we check this against the bone names we had before, they will correspond. So we actually have that many bones, not C5, but much more bones. So what if we read this table now? This diagonal arranged numbers here tells me that these are probably matrices. They are not quaternions anymore. So this big table, which is very interesting, in this game we can see both skeletons built with rotations from quaternions and from matrices. So this is a zero matrix which will represent a zero rotation. And these three numbers will be probably translations, like X, Y, and Z. So we have another bone table here. And let's try loading it up and check how it looks like. Well, it looks like something. And since I already loaded the bone names, we don't need actually bone names, but we have, when you look at this, it is actually a hand of a skeleton. These are 4 fingers, 5 fingers here. But the problem here is because they are probably global matrices. That means the numbers we read, they are not like distances between 2 bones, a bone and its parent. This is a distance from the origin. And that's why they are looking like this. That's usually how it looks like when you try loading up global matrices as local matrices. So if the format you're using can load global translations and rotations, you can just load them as globals. But for SMD, which I'm using, I need to convert these global values to locals. So I need to subtract each value for each bone between the parent and the actual bone, both rotation and translation, and save it as SMD. Well, now finally we have the correct skeleton. So in addition to a basic skeleton, we have lots of helper bones here, everywhere around arms and legs. And if we connect this now to a model, this will probably work. So that's a full model. Let's try making something. And yeah, it now works. Well, can check other bones. It will work too. Okay. So in the end, we finally have a working skeleton with all the bones connected correctly to a model. You will probably need many different ways to convert the data you are getting from files. You will need functions to convert matrices and quaternions to triangles, to convert between local and global space. You will need other conversion routines if you will need to rotate. Let's say if you need to calculate the coordinates of this bone after it will rotate to a local rotation of the parent bone, you will need a function for this. But in the end, you must be able to build the skeleton correctly and to connect it to a model. So this is probably all the information you need to do this. That's the end of the tutorial. Thanks for watching.